So hi everyone, today we are going to discuss the concepts of EMI, that is electromagnetic induction, AC circuits, alternating current circuits, and EM waves, that is electromagnetic waves. And as I have been telling in the previous classes also or lectures also, that wherever you feel that I am going a bit fast, obviously it is a live session going through YouTube, you have the facility of pausing the video or noting the important points, or you can play it at a slower speed so that you can understand it in a better way. Okay, so let's start. So first, electromagnetic induction. So what happens here, first of all we define a term which is called as magnetic flux phi b, which is a measure of how many magnetic field lines are crossing any given cross section or surface. Now that cross section can be the plane of a loop, so how much field lines are passing through the plane of a loop, that is given by what we call as magnetic flux. So mathematically we define flux just like electric flux. We define magnetic flux as the dot product of B vector and A vector, which is BA cos theta, where theta is the angle between B vector and area vector. Area vector of a loop is always taken perpendicular to the plane of the loop, and remember this area vector, when we take area vector we don't have to take the entire area, we have to take only that area which is linked with the magnetic field. Okay, I have taken some examples so you will understand. And if you see that the field lines are parallel to a loop's plane or no field lines are going through the loop, so we will say the flux is 0. Now when we take the magnetic flux to be maximum, we say that maximum number of field lines are crossing, that means the field line should be perpendicular to the plane of loop or it should be parallel to area vector, means theta is equals to 0 degree. So maximum flux is B into A. Next we have B vector. If it is continuously changing over a cross section, then we will integrate B dot dA to get phi b. Now if B vector is perpendicular to the plane of the loop, that means B and area vector are in same direction, but magnitude of B vector varies continuously, then we can write the total flux as integral B dA. Okay, so only the magnitude is changing, field lines are transverse, means perpendicular to the plane of the loop, so simply integral B dA. If we have a closed surface means which encloses some volume. So Gauss law for magnetism we get, that is the closed integral B dot dA is always equals to 0. So this shows that magnetic monopoles don't exist, magnetic poles will always exist as dipoles, so that the net value when we compare with Gauss law in electrostatics, Q enclosed by epsilon naught, here it will be total magnetic charge enclosed, that will be always 0. So magnetic flux for closed surfaces are always 0. SI unit of flux Weber or Tesla into meter square. So that's why B vector is also called as magnetic flux density. Now here if you are varying the magnetic flux for any loop, that loop can be real or you can draw an imaginary loop, like I am drawing a loop in air. Okay, just a loop, imaginary. Real or imaginary, if you are considering in a magnetic field and if you are varying the flux with time, then what happens, an EMF gets induced. This process is known as electromagnetic induction, and this EMF is induced and the process is called electromagnetic induction. If it is conducting, if the loop is conducting, then there will be a flow of current also. Okay, so that will be an induced current, and this whole process is known as electromagnetic induction. Moving on, some examples I have said for calculating flux at any instant. Suppose you can see a circular ring and the field lines are going parallel to the plane, so we will say simply flux is 0. Second, you are seeing that the field is transverse and uniform, perpendicular to plane of the ring, so we will say since it is perpendicular, directly B into area, so B naught into area of the ring, entire ring area is lying inside pi r square. Now next you are seeing, again we have a transverse field which is perpendicular to plane of the ring, but the entire area of ring is not lying, only we can see a sector area is lying, which is making an angle theta. What is the area of a sector? Theta r square by 2. Theta should be in radians, so flux here will be field into area. Why I am taking field into area again and again? Because field lines are perpendicular, B vector and area vector are in same direction. So flux is B naught into area of the sector, which is linked with the magnetic field, so theta r square by 2. Next we have a loop which is initially, you can see the field is transverse because field lines are perpendicular to the plane of loop. There is maximum flux. Initially you are seeing I have written the flux as B naught into pi r square. Now what I am doing, I am rotating it at angular speed omega, you can see. So as it rotates, obviously the area vector which is normal to the loop, it will keep on changing. Earlier area vector was out of the plane of the loop. As the coil rotates, you can see the pen is rotating. This pen is the area vector. So, or if you are not able to see my hand. This is area vector, so area vector keeps on rotating. So, at time t, the angle between area vector and B vector will change. Initially, it was 0 degree because B vector, area vector were in same direction. In time t, the angle will become theta is equals to omega t. So, we are assuming omega to be constant. So, flux will become B naught into area into cos theta, B a cos theta, B dot a becomes B a cos theta, B naught into pi r square because the entire area is inside, but angle changes, theta becomes omega t. So, this flux becomes, initial flux was B naught pi r square, so I have written phi naught, so phi naught cos omega t. So, the flux is varying sinusoidally with time. Next example we have taken over here, a long wire is there and near it I have placed a rectangular coil or loop and it is at a distance d and the length and width of the loop are shown over here. So, what we will do at x distance, now the field due to long wire varies with the distance. So, at x distance we will see that we will consider a small patch or small elementary area whose thickness I have taken dx and width is b. So, area will become b dx. So, here you can see b is continuously varying over the entire cross section of the rectangular loop. So, here we find at a general position, so b into dx will give you the flux through the shaded area. So, once we get that mu naught b value at x distance is mu naught I by 2 pi x, mu naught I by 2 pi x into b dx. This is the flux through the shaded area. Total flux we will simply integrate. X is taken from this end, that is d, to this end, that is d plus L. When you will integrate, you will get mu naught IB by 2 pi natural log 1 plus L by d, because integral dx by x is natural log. Now, Faraday's law of EMI. If the flux in all these cases which I have told, if suppose it is changing with time, then EMF induced is simply given as the negative rate of change of flux. Negative rate of change of flux means if flux is increasing, it will try to decrease the flux. If flux is decreasing, it will try to increase the flux. So, at time t equals to t, this is the instantaneous EMF. Now, this EMF is not induced as a voltage or potential difference. It is actually induced in the entire loop. It is induced in the entire loop and not between 2 points. We don't define terms like potential over here. I have explained that later also. If the loop is conducting and has total resistance R, if the loop is conducting has resistance R, they will say what is the current in the loop induced. So, I will say induced EMF divided by resistance, and the current will flow in the same sense as EMF is induced in the loop. Next, as I said, induced EMF is there, so there will be an induced electric field. This electric field is time varying. This electric field is time varying, and here it is due to a time varying flux. This is non-conservative. It is due to a time varying flux. It is a non-conservative field. It is not electrostatic field, and here we don't apply the concept of potential. We cannot define potential or potential difference between 2 points in such cases. This EMF is induced in the total loop, and we relate the induced electric field with the EMF induced as E induced is closed integral E dot dl. Now, you know, if it was electrostatic field, then E dot dl closed integral would be 0, conservative field, but it is non-conservative field, so it is not 0. This closed integral E dot dl for the entire loop will give you the total EMF induced. In a time interval of flux change, suppose you are considering any time interval in which flux is changing, the average EMF, if they ask, it is instead of minus d phi by dt, you will write minus delta phi by delta t, which is induced average current multiplied by resistance of coil. They also ask you how much charge has flown in a given time interval during the flux change. So, we know that total charge is average current into time interval, and average current, if you substitute the value, so you will get magnitude of change in flux by resistance. So, simply when they ask you find the total charge flown, you have to find the flux change, take its magnitude and divide it by resistance. Final flux minus initial flux, take the magnitude divided by R, gives you the total charge. Now, here if suppose we want to know that when can EMF be induced, so conducting coil has suppose n identical loops and B vector is uniform over the entire cross section. This we are considering over the entire cross section, it is uniform. Now, phi b at time t, if I write nb dot a, so I will write nba cos theta, where B vector and area vector are making an angle theta with each other at general time t. So, when I write E induced is minus d phi by dt. Now, there are three possibilities. Either B can change with time, a uniform over the surface, but with time it can change, or area length can change with time, or you can rotate and change the value of theta also. So, I have written overall the EMF induced will be minus n A and theta constant, so A cos theta as it is, dB by dt. B and theta constant and B cos theta constant, dA by dt. And B and A constant but theta is changing, so cos theta differentiation will become minus sin theta d theta by dt. So these are the possible cases. Now we have to remember one important thing before seeing these possible cases, that when we are finding the sense of induced EMF or induced current, whether it is clockwise or anti-clockwise in the loop, it is given by a simple law which is called as Lenz's law. Lenz's law is based on the conservation of energy. Now how do we apply the Lenz's law? Very simple method is there. What we have to do, that we have to first find the flux due to a certain field B vector. The field lines are crossing the loop, so suppose that field is B vector. So we will find the flux. Now we will check whether the flux is increasing or decreasing. So if suppose flux is increasing, how will flux increase? By increasing the magnitude of B vector or bringing the loop nearer to the source of B vector. So if the loop is brought nearer to the source, field will increase in magnitude, or if you are increasing the magnitude of field any other way also, so in such cases what will happen, more field lines will cross the loop. So when the flux is increasing, then we will assume that an induced magnetic field will be there, which will be opposite to the original field. That's it. And if you know that direction, then use thumb rule. So if induced magnetic field is into the page, right hand thumb rule. So right hand fingers will turn along the sense of EMF. Now suppose flux is decreasing with time, then you will assume that an induced magnetic field will be there for the coil or loop, which will be along or supporting the original field. If flux is increasing, induced magnetic field will oppose the original field, and if flux is decreasing, induced magnetic field will support the original field. And once you get the direction of induced magnetic field, just use right hand thumb rule, you will get the sense. I will show you by examples, it will be crystal clear. Suppose first example we have, here we have a circular loop which is placed in a magnetic field which is varying with time. We have taken this example, B is equals to alpha t square. So you can see with time it will increase. Where is flux? Into the page. Where is flux? Into the page, because field lines are into the page. Phi B is increasing inside. So flux is increasing. So what I said, B induced will oppose the original field. Original field inside, so B induced will be outside. If it is outside, see my sense, how it is going anti-clockwise. I have shown here anti-clockwise. So induced EMF, if I have to find just now the magnitude, so minus d phi by dt, just take the mod. So when you will write d phi by dt, area is pi r square, theta angle between area vector and B vector is 0 degree only. So n pi r square as it is, dB by dt will come. dB by dt magnitude you have to take, so it will become 2 alpha t. So 2 alpha t into pi r square into n, this will be the induced EMF, and sense is anti-clockwise. Next, circular coil is placed in uniform transverse field. Again, transverse field means into the page, B naught, but it is shrinking, its radius is decreasing at a certain rate given. Then if the magnitude of field is given, and when the radius becomes 5 centimeter by shrinking, how to find the EMF? See again, here original field is into the page, area is decreasing, so flux will decrease. Flux will decrease because flux is B into area. So area is decreasing, flux will decrease. So induced magnetic field will be supporting the original field. Original field is into the page, induced magnetic field will be also into the page. Then by right hand rule, induced EMF will be clockwise. So induced EMF should be clockwise. Acha, I think here we have to make this correction. Original field is into the page, so flux is also inside, it is decreasing, so it should support. So it should not be here, it should be corrected to clockwise. Okay. Now magnitude wise, here flux is B into area, B is not changing, area is changing, so B into dA by dt. So when you differentiate, pi r square will become 2 pi r dr by dt. Take the magnitude. Now don't use minus sign because we have already got the direction by Lenz's law. So you will get B naught into 2 pi r dr by dt. And now you know the value of B naught, you know the value of radius given at an instant 5 centimeter, and the rate is given 2 millimeter per second. You can put those values and get the answer. Next, we have a circular coil which I told earlier, it is rotated. So when you rotate, then in that case the flux at time t will be NBA cos theta, where theta will become omega t. I am taking n turns are there. So when you differentiate, then cos omega t will become sin omega t. So this EMF is sinusoidal. This is called as an AC voltage. This is called as an AC voltage, and this setup is called as an AC generator. So when you rotate it with constant omega, the induced EMF varies sinusoidally with time. Flux also varies sinusoidally with time. If flux is cos, this is sine. You are seeing they are varying in phase by pi by 2. So flux and EMF both are shown to be vary sinusoidally with time. The frequency of the induced EMF or the AC voltage is omega, which is the angular speed of rotation also, and the peak value, if they ask what is the peak value, you will simply say NB A omega. N is number of turns, B is the external magnetic field in which the coil is rotating, A is the area of the coil, and omega is the angular speed. This is one very important case. Next, if the loop instead of diametrical axis, we would have rotated about natural axis. If you rotate it about natural axis, at every instant you will see the figure like this only. Neither B is changing, nor area is changing, nor the angle between them is changing. So flux is constant, so theta is 0. At all instant, induced EMF is also 0. So there will, even if it is rotated like this, so axis of rotation is natural, perpendicular to the plane. So induced EMF is 0. Next, I have shown here magnet. If magnet, you know, north pole, south pole, field lines due to magnet come out of the north pole and enter into south pole outside. Okay, so when here we have taken two coils and you can see their planes, so that there is no confusion in the direction. I have already shown the direction of induced currents. We will explain how we are showing this. When this magnet is going this side, for the right side coil, you can see the field is going right side. So flux is also right side. As the magnet comes closer, flux increases. Flux increases, so induced magnetic field will oppose the original field. Where will it go? Left side. Now use right hand thumb rule. If it is going left side, see left side. So how is the current induced? See the sense. So if an observer is looking from here, he will see clockwise sense in coil 2. So I have shown here in coil 2, he will see. If an observer is here, he will see coil 2 clockwise. Now let's see this coil. South pole is nearer to the coil, field direction is towards right. Now this is moving away. When it is moving away, flux is right side for coil 1, but it is decreasing because the magnet is going away, source is going away from the coil. So flux is decreasing, so induced magnetic field in first one will be supporting the original field. Original field is right side, so it will be also right side, supporting because it was decreasing. Supporting, now see again right hand thumb rule. How the current is coming? Anti-clockwise. So if this observer is seeing coil 1, induced current, he will see it anti-clockwise. Next, very important case, if you have a metal coil or ring and a magnet is released from rest, now you can see north pole, so magnetic field due to the magnet is pointing downwards. As the magnet will approach the coil, what will happen? When the magnet will approach the coil, it is coming closer, so flux is downwards, magnetic field is downwards, so flux is downward, and it is increasing through the coil. It is coming closer. So induced magnetic field will oppose where will it act? Up. Now since it is acting opposite, so that means the coil repels the magnet, and where will it push it? Up. It will push it up. So earlier it was falling by gravity and now it is getting pushed up, so its acceleration will become less than gravity. So A will be less than G. But after crossing the magnet, after crossing the coil, when the magnet goes down, now which pole will come nearer? You will say south pole. Magnetic field is still acting down. Magnetic field due to magnet will be downwards only. Now field is downwards, but as it is going away from after crossing the coil, it is going away from the coil. So what will happen? The flux will decrease. So what it will try to do? It will try to induce a magnetic field which will support the original field. Original field was downward, so induced field will be also downward. So that means both fields are in same direction, so there will be attraction. Attraction means the coil will pull the magnet up. Earlier it was pushing the magnet up, so acceleration was less than G. Now it is pulling up. Still force, magnetic force is upward only, so acceleration will be less than G. So earlier it was pushing up, now it is pulling up. In both cases, acceleration will be less than G. So when the magnet will pass through it. Now remember, if the coil was non-conducting, if it was non-conducting, or if suppose I give a cut to the coil, there cannot be any flow of current, so there will be no magnetic force on the magnet. In that case, the acceleration of the magnet will be G downwards only. It will be simply G downwards. If you are using a non-conducting coil or a coil, metal coil, if you give it a cut, in that case I is 0, so there will be no force on the magnet by the coil, so acceleration of the magnet will be G. If they say where will there be an induced EMF? Yes. EMF is induced even if it is an imaginary loop. It does not have to be conducting. But for flow of current, the coil should be conducting and complete. Okay. So this is a very important case. Next we come. If we take this magnet and we take a long hollow metal pipe, so as it will fall down, so this metal pipe can be considered to be made up of multiple or infinite number of rings, metal rings. So some rings which it has crossed, they will pull it up, and some rings which it is going to approach, they will push it up. So overall what will happen, its acceleration will become less. Okay, acceleration will become less, and finally a stage will come lesser and lesser when the acceleration will become 0. When acceleration will become 0, it will attain a terminal speed, or it will start moving with a constant speed thereafter. So we saw in the previous case, if it is a single ring, acceleration will become less than g. But if it is a system of infinite rings placed vertically, so the rings which are still to cross, they will push it up, and the rings which it has already crossed, they will pull it up. So the acceleration will continuously become lesser and lesser than g, and a stage will come when it becomes 0. So after that it attains terminal speed. Next we have a metal ring, and suppose an electron is moving. Now we know that if electron moves, due to motion of electron, we can consider a current flowing in opposite direction. So if current is oppositely moving, means see my thumb like this, so you can see the field near the ring will be into the page, which I have shown. B due to E's motion is into the page. So flux through the ring will be also into the page. Now flux through the ring is into the page. As the electron comes closer, obviously the current will increase, flux will increase. So flux is increasing. So if flux will increase, that means induced magnetic field for the ring will be opposing the original field. So it will be outside. So how will the current be induced in the ring? Anti-clockwise. A small current in the ring will flow anti-clockwise. Now when the electron will further go away, it is going away. So flux is inside, but it is decreasing now. Now if it is decreasing, then induced magnetic field will support the original flux. Original flux is into the page. So when it supports, so that way clockwise. So first induced current in the ring will be anti-clockwise, and then it will become clockwise. Next we have this type of case, very important. Resistance per unit length of wire used in making this loops is lambda, and B vector is into the page, and they are saying that it is decreasing in magnitude with time. So flux is entirely into the page, but it is decreasing. So if it is decreasing, by Lenge's law, original field and induced magnetic field will be in the same sense. So induced magnetic field will be in this direction into the page, so EMF will be clockwise. So for both, EMF will be clockwise. But if you write EMF is clockwise, but their sense are also same here. How? That now for the bigger, always try to show the direction using the bigger loop. So if you follow this one, so see the sense, this is the sense of current. Now you can see the sense of current in both the loops are in same way. So induced current total is EL plus ER by R total. So we will add the total EMFs of both, that is capital L square plus small l square. Why? Because EMF is EMF is here magnitude. We are not changing the area, we are changing B like this. So for both you will see area for first one is capital L square, next one is small l square. So L square plus small l square into dB by dt is common for both, magnitude divided by total resistance. Resistance per unit length of the wire is lambda. Total length of this loop is 4L, this loop is 4 small l. So lambda into 4 capital L plus small l. But if you see the second case, we have formed again a loop, but by twisting it. So if you twist this, both senses are again same, EMF same, but here you will see when you write the induced current, it is EL minus ER. Why? Because if you try to make the current flow, see here what you will see, always follow the bigger one. So when you see the bigger one, now you will see that in this loop, bigger loop, so it is clockwise, but in this one it is anti-clockwise. It is anti-clockwise, whereas EMF induced in the smaller one is clockwise, current is anti-clockwise. So we will take EL, E left minus E right by R total. So E left minus E R by R total. So here instead of addition there will be subtraction of the areas. So capital L square minus small l square, denominator will be same, total resistance, and into dV by dt. So this is one important case which you should be remembering. Next, types of EMI in conducting loops. One is self-induction. Suppose a coil like this, like a solenoid, it is carrying a current I. So its magnetic field I have shown here, the field lines you can see. So these field lines are passing through the plane of the or cross section of the solenoid like this. So flux, we will write total number of turns B dot A, where A vector is for a single loop. So there are n loops, so n into B dot A. Now we know that field due to a solenoid mu naught Ni. So field is always proportional to I. So total flux is also proportional to I. I have written total flux as Li. This L is called as self-inductance, which is also called as the electrical inertia. This L property, this always opposes not the current, change in current. Resistance opposes current, this opposes change in current. So it is called electrical inertia, self-inductance of the coil. SI unit is Henry. Now here we have to remember one important thing, that current, if suppose it is changed with time, then if current will change, so flux will change. So induced EMF is minus d phi by dt, so you will get minus L di by dt. So total flux due to all the turns, that is equals to Li. So induced EMF is minus L di by dt. L, I said electrical inertia. Such type of coils are given a name in electrical circuits. We will call them as inductors. Now for inductor, how does it behave in an electrical circuit, that to DC circuit? So suppose at an instant we have an inductor coil, current is I, inductance is L, self-inductance. Suppose current is increasing. If current is increasing, di by dt positive. Di by dt positive, so what it will try to do? It will try to decrease the current. So it will behave like a battery. See the polarity, very simple. Current is going right side, so it will try to decrease it. If it is increasing with time, it will try to decrease it. How it will decrease? It will behave like a battery like this. Polarity positive first, negative second. You will say, sir, why? Simple. It has to oppose the current. So you know general trend of a battery is to send current out of the positive terminal. So due to this inductor, it will try to send current left side and original current is right side. So it is getting opposed. That's it. And you will take the value of VL as mod of L di by dt. Don't be confused with, sir, what sign and all. Just mod L di by dt. And which is at higher potential, A will be at higher potential than B. If current is decreasing, it will try to support it. Original current is going right side, so it will also try to send current right side. So see the polarity. Right side polarity will become positive, trying to send current in the same sense as original. So it will try to increase the current. So here VL will become VB minus VA. Again mod L di by dt. If current is constant, there is no change, di by dt is 0, steady state we call it. In inductor, steady state, it will behave like a wire, resistanceless wire. All points will be at same potential, potential difference will become 0. Remember this very important thing. Current is maximum in such case, current becomes constant, steady state, inductor behaves like a wire. Next, an example we have taken here, we can see a branch of a circuit, a part of it between points P and Q, where current I have shown is flowing left side, and I have taken a 4 volt battery and 2 ohm resistor, 50 Henry inductor and 12 volt battery again. They are arranged as shown. Now at the instant shown, they have given that at particular instant current is 2 ampere and it is in decreasing at a rate of 0.1 ampere per second, going left side and decreasing. So first I said directly find VL. Inductor will behave like a battery whose EMF will be mod of L di by dt. L is 50, di by dt is 0.1, so it will become 5 volt. Now redraw the circuit branch. 4 volt, 2 ohm, 12 volt as it is I have drawn. Now see how I have shown the inductor as a battery. Current is left side, it was decreasing, so it will support it. It will also try to send in same direction. So see the polarity, I have taken left side positive so that it also sends in the same direction. That's it. Now write Vp minus Vq by KVL, simple KVL. Vp minus Vq, you are hitting the negative terminal first, minus 4. Current is opposing me, current is coming like this, I am going P to Q. Vp minus Vq means go from P to Q. So minus 2I. Then I am seeing positive terminal of this battery plus 5. Then I am seeing positive terminal of this battery plus 12. We get 9 volt. This is the potential difference. Self-inductance of an ideal solenoid. When you use the concept of finding flux, total flux due to a solenoid NBA and put the value of B as mu naught small n I, you get the self-inductance formula as mu naught n square V, where V is the volume of the solenoid, pi r square length, and small n is number of turns per unit length. Very, very important formula, remember this. Next, energy and energy density. The magnetic field inside the solenoid or the inductor will store energy in that region. That stored energy is of the form half Li square. Just like in capacitor we have half CV square, here we have half Li square. And energy per unit volume is called as the energy density. Energy density becomes UL by volume, and when you substitute mu naught Ni as capital B naught, you get this as B naught square by 2 mu naught, where B naught is, I said, mu naught Ni. So energy density in magnetic field can be remembered by this important formula. Even though it is derived for an inductor, it is valid in all cases. At a given region where the magnetic field is B, there the energy density is B square by 2 mu naught in free space. Combination of inductors. If you have inductors combined in series, just like resistance, L equivalent, you will take L1 plus L2 plus L3. If they are connected in parallel, current will divide into different parts, but 1 by L equivalent is 1 by L1 plus 1 by L2 plus 1 by L3. Just like series and parallel combination for resistors, similar we have in inductors also. Next, second type of induction is mutual induction. When we were talking of a single coil, due to its own current, if it is changed with time, you get self-induction. If you have two coils which are linked completely or partially by a common flux, for example, one coil is carrying current and its magnetic field lines are passing through both the coils, nearby placed coils. Then when we induce a EMF in one of the coils by changing the flux or changing the current in other coil, it is called as mutual induction. So we can say that suppose we have these two coils, coil 1, coil 2. Here you can see I have made a setup where I have connected a battery and a variable resistor by which we can change the current in coil 1. Generally, the coil which is carrying current and which you are changing, it is referred to as primary coil. And due to it, which one is having EMF induced in it, that is called as a secondary coil. So here we will say coil 2 is secondary, coil 1 is primary. So coil 1 I am taking current like this, so its magnetic field lines will go this side. So it is passing through both the coils. So when it is passing through the coil 2 also, now suppose current I1 is changed. When we say flux through the second coil, due to the current of coil 1, we will write flux phi 2 as number of turns in second, whose field we are considering, field of first, B1, through whose area it is passing, coil 2. So B1 dot A2. Now this whole flux will depend on B1 and B1 will depend on I1. So it is directly proportional to I1. So here the flux in the coil 2 due to the field of first coil is MI1. This M is called as mutual inductance. Due to single or self, we call it as self inductance. This is due to second one, so we call mutual inductance. It is always defined for a pair of coils, not for a single coil alone. So phi 2 is MI1. Now suppose I1 is changed with time, then EMF induced in the second one will be minus d phi by dt, which will become minus M di1 by dt. Second EMF, first current's rate of change. So this is mutually induced EMF in coil 2. Now suppose what if I take the coil 2 as primary, that means its current is varied, that is its magnetic field is linking coil 1, then coil 2 will become primary, coil 1 will become secondary. So I will say flux in first coil due to what second one is Mi2. Mi2, so induced EMF in first coil, mutually induced EMF will become minus M di2 by dt. So this M value remains the same for both. Okay. SI unit of M, just like self inductance, it is Henry. When we have a pair of coils which are mutually coupled, their flux are linking each other, we relate M and L as M is K times under root L1 L2. L1 L2 is self inductance, K is called as coupling constant. When there is complete flux linkage, entire flux of first one goes through the second one. In that case, K is 1. Maximum we get the value of mutual inductance, which is root under L1 L2. So maximum flux linkage, mutual inductance for a pair of inductors is root under L1 L2. When we have pair of ideal solenoids which are coaxial, suppose we have placed one over the other. Smaller one is inside, you can see, larger one is outside. Common length between them is L. The radius of cross section of smaller one small r, larger one capital R. In self inductance of a single inductor, you saw it was mu naught n square volume. Here when we use the concept of finding mutual inductance by flux, M comes as mu naught n1 n2 V inner, means number of turns per unit length in smaller coil, small n1, number of turns per unit length in larger coil, small n2, V of inner solenoid is pi small r square L. So we have to take the common area for both. What is the common area? You will say common area is the inner one. Inner area will be common for both the coils. So volume comes as common area into length, which is pi r square into L. Very, very important. Important examples I have taken here, like suppose we have a pair of two circular coils, coil 1, bigger one N1 comma R, and small coil 2, whose radius is small r, very small, it is kept near the center. So in this case, if I take the coil 1 as primary, so due to that I have found the flux through the inner coil, knowing that the field due to large coil at the center will be mu naught Ni by 2r. Using this concept and separating I1, so we are getting the value of capital M. You can pause and see what is the value of capital M here, and we can remember capital M is directly proportional to small r square, radius square of the smaller coil divided by radius of the larger coil. Same concept if we use for a square loop and there is a small square loop inside, so outer and inner. In this case also mutual inductance will be proportional to, just like here, square of the size of the smaller divided by size of the larger. So small l square by l. This is asked in objective questions, you can directly answer. Next we come to motional EMF. Motional EMF, when we have a conductor, it is moving or made to move in a transverse magnetic field. So if it has a length L, velocity V, so what happens? There is an EMF induced. There is an EMF induced in this, and positive and negative polarities appear at the ends of the rod. So Vp minus Vq, if you see in this case, here we will see that suppose the rod has some internal resistance also, but here it is just like an open circuit, it is not part of a complete circuit. So we will just say that P is at higher polarity than Q, and the EMF induced is BVL. B is the magnetic field, V is the speed or velocity, L is the length. Now important points, how to know which polarity will be positive, P or Q, which one is at positive. Simplest method, just see the velocity, put your right hand, turn towards B vector, V cross B. So V is right side, B is into the page. So where is my thumb going? Up, so upward will be positive. So V cross B points towards positive terminal of induced EMF. Now in this formula, when you are using BVL, mind it, all the three terms should be mutually perpendicular. If any two terms become parallel to each other, EMF will be immediately zero. If the conductor is of any other shape like curved, then also you have to take all the three terms perpendicular. So BVL effective. So suppose we have taken a curved conductor like this, it is moving towards right. Magnetic field I have taken outside. So you can see every V and B are to perpendicular. So we have to take the length between the two ends, which is perpendicular to V also. B to naturally it is perpendicular because it is perpendicular to the page. So L should be made perpendicular to V. So we will take this length, this part. So L effective. So now polarity wise, V cross B. V is right side, B is out of the page. See. So where will be the positive polarity? Q will be positive. So EMF is BVL effective, VQ minus VP. Next, we have taken this case, important one, when we have this rod, conducting rod sliding down. So if you see the side view, things will become very easy to understand. You will see the point Q. Now magnetic field is upward in the region, velocity is down the incline, length is into the page. Now L and V are mutually perpendicular, but magnetic field is not perpendicular to velocity. So we have to take components of magnetic field, one component which is perpendicular to the inclined plane, that will be perpendicular to velocity also, that is B perpendicular. Now if this angle is theta, this angle will also become theta. So B perpendicular will become B cos theta. So we will get EMF will be B cos theta into V into L. Now which one is the positive polarity? Again simple, V cross B. See where is V? V is going down the incline. Where is B? Up. So positive polarity will be into the page. Into the page, outside was Q, so into the page is P. So it will become Vp minus Vq. Okay. Now if this moving conductor forms part of a closed circuit, for example we have a smooth conducting rails, long rails, there is transverse magnetic field uniform, the separation between the rails is L, here we have connected a resistance which is load, and we are taking this rod, at any instant its velocity is towards side V, its mass is M, length is L, internal resistance also it can offer in the circuit Rin. Now here when we redraw the circuit, we know that EMF will be induced BVL at this instant. So due to this a current will flow, which we can find EMF by total resistance, which will become BVL by R load plus internal resistance. Now they will say what is the power delivered to the load? Simple, power delivered to the load is I square into resistance of the load, right? We know I, we can find this. Now forces on the rod, since current in this circuit will turn and in the rod it will go from Q to P, you can see up. Now there will be a magnetic force IL cross B. We have studied IL cross B. I upward, B is into the page. So IL cross B is left side. So this force will be always opposite to its velocity. Remember, this force is always opposite to velocity. So it will retard it by retardation, force by mass. Now this retardation I can write as minus dV by dt. And if I put the value of F as ILB, where I is substituted, so we get B square L square by M into R plus RV is equals to minus dV by dt. When you will integrate both sides by taking dV by V, it will come exponential. So V will come in the form V naught initial velocity into e to the power minus gamma t. So where gamma B square L square by M R plus R. Now this shows that when you connect this rod across a resistor, then the kinetic energy of the rod will drain off, and that energy will be dissipated in form of the heat across the resistances in the circuit. So the velocity of the rod will exponentially decrease and finally become zero after long time. Now if I don't want it to decrease exponentially, so what I have to do, in the beginning only when its velocity was V naught, that time the force on the rod will be ILB, which will become B square L square V naught by M R plus R. If I apply the exactly same amount of force along the direction of motion, so that force will balance this magnetic force. So net force will become zero, it will move with constant velocity. So whatever magnetic force was acting at t equals to 0, that much external force we have to apply in the direction of velocity, then it will be moving with constant velocity. Two examples we are taking, like here we have a resistance which is fixed. We are taking two rods, one is moving this side, one is moving this side. They are asking what is the current through the fixed resistor at the instant shown. How can we find it? See, these two will behave like batteries. So directly we can redraw the circuit. Now here BVL, so field is out of the page, so BVL down positive, we just explained. It has got internal resistance also, and this side V cross L up positive. This is R. Plus minus BVL. They have given V naught and B V naught L. Internal resistance is given for this side as 2R. For this side BVL, if you put, it will become 3B V naught L, and the resistance this side is given as 3R, right? Now this we have to find. Let's call this as EF. So simplest way of finding this current. Now we can see these two are parallel. Now these two are parallel. We can replace the whole by a single cell, two cells in parallel. Instead we can take three cells in parallel. Why? Because this is also a cell with zero EMF. So we can use the formula of parallel cells, and you can see E by R ratio, here comes 1, here is coming 1 by 2. So this one is dominating. So we can redraw EF. This is R equivalent, this is E equivalent. So directly you can make it as an open circuit. This side plus, this side minus. So this polarity is dominating, so according to that I have substituted. So what you will say, F is at higher potential, so VF minus VE will become equals to E equivalent. VF minus VE is E equivalent. What is E equivalent? Put value this, E1 by R1. So this will become BV naught L by R, E1 by R1. Here we don't have any EMF, 0. Here we have opposite EMF, so minus BV naught L by 2R. If you know the formula for parallel cells, you won't have any problem in this, divided by 1 by 3R plus 1 by R plus 1 by 2R. So from here ultimately current is asked through the resistor R. We can say it is simply VF minus VE divided by R. So we got VF minus VE from here. which will become B V naught L by R minus B V naught L by 2R, which will become B V naught L by 2R, and in denominator we have, taking LCM as 6, so 2 plus 3 5 plus 6 11. By 6, and here we have one more R. So I'm sorry, this R goes up. So we have 2R into 11, and this R and this R will cancel, only one R will be left. So we will have 3 B V naught L by 11R. This will be the current. You can cross check it. Next, we have a long wire, and you will see a loop is placed in a rate, and at a certain instant it is at x distance. Here its length is B, this length is L, the speed is given as V naught. They are asking what is the induced EMF. Now you can see that as the loop will move, this arm and this arm, their lengths are parallel to velocity, so no EMF will be induced. EMF will be induced only in these two arms. Both are moving towards right. Now original field due to the wire will be into the page. So if you see V cross B upside will be positive. So in this question directly EMF will be induced only in two arms, and both will have upward positive polarity. So that's it, like this you will write. So here we have E1 whose sense is like this, here we have E2 whose sense is like this. E1 will be for this arm, whatever is the magnetic field due to the wire, let's call it as B1 into V into length of the arm is B. Here we will have B2 into V into B. Now what is B1 and B2? Very simple. B1 is the magnetic field at x distance, which is mu naught I by 2 pi x into VV. If you see B2 is the magnetic field due to long wire at what distance? L plus x. So it will become mu naught I by 2 pi L plus x VB. Now which one is more? You can see obviously E1 is more than E2. So E1 is more than E2 and their senses are opposite. So we will say EMF in the loop will be E1 minus E2. So you can take just the terms common, mu naught IVB by 2 pi common, it will become 1 by x minus 1 by L plus x. That's it. So this will be the EMF induced in this loop. Clear? Next, if instead of linear motion where there is a rotation of the conductor in transverse magnetic field like I have shown, so every point of the conductor will perform circular motion about the axis. So if we have a conductor whose length is L and here it is rotating at omega, so EMF induced between the two extremes, one is the extreme periphery and other is the axis. So that EMF will become B omega L square by 2. Now which one is positive, which one is negative, how to know that? Again very simple, see the sense of omega. According to that you can see the velocity. If it is rotating like this point will have a velocity like this. So V cross B again, velocity cross B, this is positive terminal. So A will be positive with respect to O. So VA minus V axis we have taken. One point is end point, one point is axis point. It is B omega L square by 2. Now if you have conductors of different shapes, you will replace L by L effective. What is L effective here? Whatever is the end point or the periphery point, just you have to first check whether there is at least a single conducting path joining the extreme point to the axis point. For example, here to here you are seeing a conducting path. So if conducting path is present, then simply take the shortest distance or straight line joining the two points, axis and the end. That length will be taken as L effective. This should be remembered. Okay. So B omega L effective square by 2. I'll make it simple by these examples. Suppose we have a L shaped rod. This end is A, this part is of length B, this part is of length A. It is rotating. Now, which will be taking from O to B, we have one conducting path, complete conducting path. Can you see? Yes. If that thing is okay, then join this and this directly. So this will be called as L effective. L effective here by Pythagoras theorem will be under root of A square plus B square. Now, which is at higher potential again, omega is like this, B is into the page. So B, capital B will be at higher potential than O, which I explained just now. So B omega L effective square will become A square plus B square by 2. Second example I have shown here, I have taken field again into the page. Now I am giving it a rotation anti-clockwise, but axis is not at the end, axis point is here. This point is the axis. Now this is axis. So here always this formula B omega L square by 2, one of the point is periphery, one is the axis point, remember. Now if you see, where will be the direction of velocity of P? P velocity will be like this and Q will be going up. So if you use again V cross B, V is up, cross B, V cross B, this side positive means O will become positive and Q will become negative. Same will happen here also. When you see V for P is down, cross B positive, O is positive, P is negative. So in both cases, O axis point is at greater potential than the end points. So I am writing the formula separately. VO minus VP is B omega A square by 2. VO minus VQ is B omega B square by 2. Now if you can subtract both or add both, whatever you do, you will get the potential difference between the two ends. Next example, very important, if you have a disc, metal disc, and it is rotated about its natural axis. Now here they ask you what is the EMF induced between the center and the periphery. So I will say that is there at least one conducting path. I will say infinite paths are there from center to periphery, all have radius r. So you just have to replace it by a L effective value equals to r only. Or if you have a round spoke ring with large number of n number of metal spokes, then also do you have conducting path from center to the rim? Answer is yes. So L effective in each case is capital R. So L effective in each case is capital R. So we will say periphery and axis potential difference will be B omega R square by 2. That's it. So very important examples for rotation. Next we come to alternating current. Alternating current, any current signal or voltage signal which fluctuates periodically with time, both in magnitude and direction. General AC signal when we represent, whether it can be I or V. When I am writing small I or small v means it is denoting the instantaneous value of current or voltage. So every time writing I or V I am writing as X. X can denote current also, voltage also. So it is a function of time. Now in general for any signal, if it is X as a function of time, in any interval if they ask you from T1 to T2, find the RMS and average value. Average value or mean value is defined as just integrate the signal with respect to time and divide by time interval, which you can also, if it is linear graph, then directly you can say area under xt graph divided by time interval. Otherwise you have to integrate. If they ask you RMS value, then instead of integrating x, you have to integrate x square with respect to time in that given interval T1 to T2, divide it by T2 minus T1 and then take root. This is called as virtual value or effective value of a signal. Why it is called, we will understand later. RMS value is also called as virtual or effective value of a signal. Now, if it is a sinusoidal AC signal which is of the form x is equals to x naught sin omega t plus phi, x naught is called as the peak value. For half cycles, when you will integrate, you will see that the average value of the signal, whether current or voltage, it comes as 2 times peak value by pi, whereas the RMS value comes as peak value by root 2. For full cycle, if you see, average value will be 0, positive and negative half cycles will get cancelled, average is 0, but RMS you are doing square, so it doesn't cancel, it becomes same, whatever is in half cycle it is in full cycle also. For sinusoidal, full cycle or half cycle, RMS value is x naught by root 2. For example, RMS current I naught by root 2, RMS voltage V naught by root 2, right? In terms of peak values you can write this value. Important results, if you have a signal which is of the form of DC plus AC, A plus B sin omega t plus phi. Now A is a DC value, constant value, and B sin omega t plus phi. They will ask you what is the RMS value of the signal. You can integrate and find, but you can save your time by under root of whatever is the DC value, square it, plus this AC value, find its RMS value and square. So A square plus this one's RMS value square. RMS value is B by root 2. B by root 2 ka square under root. So it will become A square plus B square by 2 power 1 by 2. Next we are having, if you have both sinusoidal A and B, here X RMS under root of RMS square of first signal, RMS square of second signal. First signal A by root 2 RMS value, B by root 2 for second one. So A by root 2 square plus B by root 2 square under root, which will become root under A square plus B square by 2. Clear? Now if you have two signals and you see both are in sine or both are in cos, so when you subtract their phase angles, we get what is called as phase difference. Okay, whichever has more phase angle compared to the other, we say that signal is leading, and whichever has lesser phase angle, we say it is lagging. For example, cos and sine, cos always leads sine by pi by 2. So if suppose we have an AC circuit and they have given that current is I naught sine omega t and voltage is given V naught cos omega t. Now we know cos omega t can be written as V naught sine omega t plus pi by 2. So sine omega t, and here you are getting sine omega t plus pi by 2. So who is leading? Voltage is leading. We will say voltage will lead current by pi by 2, or current will lag behind voltage by pi by 2. When we have constant signals, if you have constant signals, average value, RMS value both are same, equal to that signal value itself. Example I have taken, suppose we have a signal which you can see linear, but first increases to a max, then opposite in direction again increases, so linear signal is given. If I find for half cycles 0 to t by 2, I can write the equation of this current y is equals to mx form, so I is equals to 2 I naught by t into small t. So when I find I average, I can take area of the triangle divided by time interval t by 2, so I will simply get I naught by 2. If I want to find the RMS value, I have to integrate I square. I will integrate this square, divide by time interval, take under root. I get this by I naught by root 3. If you do the same for 0 to capital T, so 0 to capital T, positive and negative half cycles will cancel, so average value you will get as 0. Whereas RMS value you will get the same as I naught by root 3. In sinusoidal you were getting I naught by root 2, here you are getting I naught by root 3. Next example I have taken, here we have square pulse but not AC. It is, you can see it not becoming negative, only positive. First 0 to t by 2 you are having V naught, again you are having 0, then again you are having V naught. Now it is repeating itself after this time capital T. So if I take from 0 to t by 2, the average value and RMS value both will be same because V is constant. So both will be same as V naught only. But if you take from 0 to capital T, in that case if they ask you average value, so what I will do, I will find area under the graph. But you see area under the graph is only up to 0 to t by 2. After t by 2 to t, the area is 0, there is no area. But you have to divide by the total time interval capital T. So V naught into t by 2 plus 0 by t, which we get as V naught by 2. But if you find RMS, you have to integrate V square. So from 0 to t by 2, it is V naught square. But from t by 2 to t, it is 0. So when I integrate and divide it by the total time interval and take under root, I get the RMS value as V naught by root 2. So this is the method of finding RMS and average values. Now AC signals, whenever we measure them by the help of special meters which are called as energy meters, which is based on finding the total heat produced by these signals when passed through a resistor. If you try to measure them by ordinary DC voltmeter, ammeter or galvanometer, you will get 0 reading because they read the average value, and average value per cycle of AC we know is 0. So it will give 0 reading if you are using AC signals passing through a DC voltmeter, ammeter or galvanometer. So one important thing, if you apply a constant DC signal across a resistance R for long time, you will see heat will be I square RT. So I square RT or V square by R into T, where I is IDC, V is VDC. But if you apply AC signal, then it is varying, so you will have to use integration I square R dt. So when you integrate and find, you will see heat comes as I RMS square R delta T or V RMS square by R delta T. Means that's why it is called as the effective value. When you integrate the total signal, you are integrating actually this I square R dt from T1 to T2. But when you integrate, you know integration I square dt from T1 to T2 can be written as I RMS square into delta T. So finally in the expression, you are not getting the entire current, only the RMS value. That's why it is called as effective or virtual value of AC signal. So I RMS square R delta T or V RMS square by R into delta T. This is the heat AC circuits, sinusoidal signals will be considering standard in our country 50 hertz frequency AC signal is generated. This should be remembered. If you go to US, it is at 60 hertz. So if supply voltage V and circuit current, they differ in phase by phi. In a circuit, suppose current and voltage differ in phase by phi, then at time t, if they ask you instantaneous power, you will simply write I into V. But if they ask you average power per cycle of AC, then by integration it comes, integrating power with respect to time and dividing by time interval. Average power comes Vrms, Irms cos phi. Now every time, no need of writing Vrms, Irms like that, you can write capital V, capital I also. If capital V, capital I are written, means they are RMS. But in terms of peak value, Vrms is V0 by root 2, Irms is I0 by root 2 for sinusoidal signals. I have already mentioned sinusoidal. So V0, I0 cos phi by 2 also we can say. So by integration, if they differ in phase by phi, then average power will be expressed in this form. Extra cos phi is also coming. Now when we write P average, it is called as Q power or wattful power. It is always measured in watt. Whereas if you just multiply RMS voltage and RMS current, it is volt ampere. It is called as apparent power. This is not the true power. This is called as apparent power. Both are related to each other. So cos phi here is called as power factor. Vi is apparent power. When you multiply Vi by cos phi, then you get the true power. So cos phi is given the name power factor. Out of the total theoretical power, how much is actually appearing, that is called as, that factor is called as power factor cos phi. For AC circuits, very important role, if phase difference between voltage and current, which is phi, is 0, power factor will become 1. So in that case, we will say that voltage and current are in phase. Voltage and current are in phase. Then the ratio of RMS voltage by RMS current or voltage by current is equals to R. We call, then only the ratio is called as resistance. But if phi is pi by 2, that means current and voltage are having a phase difference of pi by 2 between them, power factor will become 0. RMS voltage by RMS current or peak voltage by peak current now won't be known as R. It will be called as X. Unit is same because voltage by current, same unit ohm, but it will now be called as X, reactance. There are two types of reactance, one is inductive, one is capacitive. If you see that the voltage leads the current by pi by 2, it is the ratio XL. We call it as inductive reactance, whose value is given as omega into L. Omega is the frequency of AC, L is the inductance. Now here, if current is leading the voltage by 90 degree, then we say that the voltage by current is XC, which is given as 1 by omega C. Mind it, whenever we are drawing diagrams like this is called as a phasor diagram. This is called as phasor diagram. And in phasor diagram, while you compare, we compare only the RMS values. And whichever is in anti-clockwise, that is said to lead. Now, from voltage to current, you are seeing anti-clockwise. From current to voltage, you are going clockwise. Anti-clockwise will denote lead, clockwise will denote lag. When you are comparing two signals in phasor diagram, see from one signal to other whether you are going anti-clockwise or clockwise. If you are going anti-clockwise, that means going to lead. If you are going clockwise, means lag. So here current leads, voltage lags. Here voltage leads, current lags in inductor. Clear? Next we have, if in general the phase difference is in between 0 and pi by 2, so power factor is less than 1. So this is called as a mixed circuit, means there are more than one element. There are inductor, capacitor, resistance, other things can be also present. Inductor, capacitor combination, not other things, their combinations can be present. So in that case, when you take the RMS voltage by RMS current or peak voltage by peak current, now you won't be calling it either R or X, you will call it instead as Z. It also has a unit ohm, it is called as impedance of the circuit. And Z is equals to under root of R square plus X square. Cos phi power factor is defined here as R by Z. And tan phi, another way of finding the power factor is cos phi. How to find phi, the angle between voltage and current? Tan phi is X by R. Now average power formula we know, Vi cos phi. Vi can be written as V by Z and cos phi can be written as R by Z. So sometimes this form is also asked. So average power can be written as V square R by Z squared. Very important thing, when we have mixed circuits, like examples RC circuit. RC circuit, here we know voltage in the resistance is always in phase with current, And current and capacitance, we know that current leads the capacitor, I have told. So you will see that in RC circuit, current will lead voltage by phi. So current is here, net voltage is downward. So net voltage is the magnitude of the resultant of VR and Vx, which is under root of VR square plus Vx square. VR is IR, Vx is IXC, V is IZ, where Z is under root of R square plus X square. LR circuit, voltage leads current. Whenever inductor is there, voltage leads. Whenever current is there, capacitor is there, current leads. Now if it was only a capacitor, then current would lead voltage by 90, but there is resistance and capacitance both. So current is leading by small angle phi. Here also voltage is leading the current but by phi, not by 90, because we have inductor as well as resistor. So V is equals to IZ, Vx is IXL, VR is IR. Okay, and you can find tan phi by X by R. When we have this part, I think I already told. Okay, now next, LCR circuit. Suppose all the three elements are present. Then in that case, what you will do, you will take X as XL minus XC if XL is more than XC. So whenever inductance is more, voltage will lead. So here also we will say voltage is leading current by phi. And if X is greater than, XL is greater than XC, so that means omega L will be greater than 1 by omega C. So we will say omega is greater than 1 by root LC. How we will understand whether the circuit is more inductive or more capacitive? Just find 1 by root LC. So if omega is more than 1 by root LC, so XL will be more than XC. Voltage will lead current by phi. Next, if XL is less than XC, how will you understand if omega is less than 1 by root LC? In that case, what will happen? In this case, current leads voltage by phi, and everywhere same rule, that all things don't forget, tan phi is X by R, cos phi R by Z, Z I already told, under root of R square plus X square. What is X here? XL minus XC in first case, here it will become XC minus XL if XC is more. And if XL and XC both become equal, then X will become 0. X becomes 0, voltage and current will come in phase, that is power factor will become 1, phi will become 0, circuit will become purely resistive. Even though inductance and capacitance are there, their effects will cancel each other, circuit becomes purely resistive. This will occur when omega will become equals to omega naught 1 by root LC. So this is given a name, omega naught, we call it as resonant frequency. We will call it as resonant frequency. At this frequency, voltage and current will come in phase. Maximum power you will get, power average was VI cos phi, you will get VI, which is V square by R, maximum. Z under root of R square plus X square will become equals to R, which is minimum value of Z, and current will become maximum. The circuit draws maximum current at resonance, and the impedance becomes minimum. Also, here we define two more important frequencies. One are called as omega 1, omega 2, which are called as half power frequencies. Half power frequencies are those frequencies when the average power will become half of the resonant power. Resonant power P average was V square by R. So when power will become half, means current will become 1 by root 2 times. That frequencies we call as omega 1, omega 2. Why I am calling two values, not a single value, you will understand. When you have omega as omega 1 and omega 2, power becomes half, Z current will become 1 by root 2 times, so Z will become root 2 times of the resistance. That means at half power frequencies, X will become equals to R. Now X can be written, I said in LCR circuit, X can be XC minus XL also, XL minus XC also. So at one frequency, omega 1, which is less than resonant frequency, we know capacitive reactance is more than inductive reactance, circuit is more capacitive. Then X will be XC minus XL, and this value will become equals to R. At which frequency? Omega 1, at this half power frequency. Another half power frequency which is more than resonant frequency, there X will be XL minus XC, because circuit becomes more inductive, this will become equals to R. When you find both by quadratic equations, you will solve and easily get omega 1, omega 2. When you take their difference, we get it is equals to R by L. Very important formula. It is called bandwidth. And when you take the geometric mean of omega 1, omega 2, that is root omega 1, omega 2, you will get the resonant frequency omega naught. So very, very important results. Important graphs. If you see XL is omega L, XC is 1 by omega C, and resistance is independent of omega. So XC versus omega variation is rectangular hyperbola, XL versus omega is a straight line passing through origin, and R constant graph. if you see the current variation, RMS current in the circuit with omega, if you change the frequency, so current will start increasing, it reaches peak value at resonant frequency and then again decreases. I have shown the two half power frequencies omega 1, omega 2 on both sides. I said this gap is called as bandwidth, and this half power frequencies current becomes 1 by root 2 times, sorry, 1 by root 2 times of the peak value of RMS current. And if you draw the graph of Z, just opposite of I, so Z will become minimum at omega naught, and at omega 1 and omega 2 it will become root 2R. Next, one more term we define, which is called as quality factor of resonance in LCR coil. So whether the resonance is obtained clearly or not, that is checked by quality factor, which gives the sharpness of resonance. So Q value at resonance is defined as, at resonance we know VL and VC will become equal because XL and XC becomes equal, and VR and V becomes equal. Total voltage will become equals to VR. So VL or VC, whatever you write. So I have written VL equals to VC. So whichever you can take divided by V. So you will get XL or XC divided by R. So if you put here omega naught L by R, you know R by L I said bandwidth, so quality factor can be defined as omega naught by bandwidth. Resonant frequency by bandwidth is quality factor, inversely proportional to bandwidth. Very, very important point, it is inversely proportional to bandwidth. Also, if you put the value of omega naught as 1 by root LC, you will get quality factor in terms of 1 by R root L by C. So they ask you in question, if I increase capacitance, inductance or resistance, how will quality factor change? You can see this result. Bandwidth, if I have compared two coils which has more bandwidth, like you can see coil 2 has more bandwidth than coil 1 is sharper. So comparing two coils, whichever has more bandwidth, its quality factor will be less. Whichever has less bandwidth, its quality factor will be more. Other important terms we have power triangle. Three types of power we define, out of which actual power is VI cos phi. The product of V and I, these are RMS values. I said it is called as apparent power. So when I take VI cos phi in this triangle, I get VI cos phi, it is true power. And when I take this side, VI sin phi, it is called as reactive power. So units, whenever they ask you true power which is VI cos phi, it is always measured in watts. It is always dissipated across resistor. Apparent power is just the product of voltage and current, RMS values. Its unit is volt ampere, VA, volt ampere. And when you see VI sin phi, it is called as reactive power because of reactive elements like capacitor and inductor. So this one is having a unit volt ampere reactive. VAR means volt ampere reactive. One more term is used which is called wattless current. Sometimes they will ask you what is the wattless current. If current and voltage they differ in phase by phi, then take the component of current which is perpendicular to voltage. So if voltage and current are perpendicular in phase, that means the power will be 0. P dot means average power will become 0. So the current component which is perpendicular to voltage in phase, which is I sin phi, it is known as wattless current. So if the phase difference between voltage and current is phi, then I sin phi is called as wattless current. Remember this. One more term, sometimes they can ask you form factor. Whenever you are taking the RMS value of a signal and divided by the mean value or average value, it is called as form factor. Very, very important. Small terms should be remembered. Next we come to the last part of this chapter, which is electromagnetic waves. Electromagnetic waves, they travel in space, they don't require a material medium for propagation. So such waves are represented by their wave function either in terms of electric field or magnetic field. Time varying, oscillating magnetic and electric fields are there. Y as a function of x and t. If x is the x axis is taken as the direction of wave, then electric field at a position x equals to x at t equals to t is E naught sin kx minus omega t. So magnetic field will be B naught sin kx minus omega t. But their fluctuations are not in the same direction. Their E vector and B vector and the velocity of the wave, all the three are mutually perpendicular. So E vector, B vector and V vector of EM wave are mutually perpendicular. How to know what is the direction? So they are related by a vector which is called as pointing vector, S vector. S vector is pointing vector which is defined as E vector cross B vector by mu naught if you are talking in free space. If you are taking in any other medium, you will replace mu naught by mu. Now here velocity of the wave is always along Poynting vector. So in short we can say that the electromagnetic wave velocity is always in the direction of E cross B. So in questions where I cap, j cap, k cap form are given, just take cross product of E and B, that will be the direction of velocity. Vibrations of E vector and B vector are always in phase. Whatever you are seeing phase angle here, same phase angle here. Their directions are mutually perpendicular, but their vibrations are always in phase. When you find the velocity magnitude of EM wave in any medium, so what you can do, just divide E by B. So Maxwell and Ampere found that V is equals to E by B, E naught by B naught, and omega by K, all are same. In vacuum, speed is c, it is given by 1 by under root of mu naught epsilon naught, whereas in medium it is 1 by under root mu epsilon. Refractive index of a medium we know for light, refractive index of medium Snell's law, c by v. So c by v is under root of mu r epsilon r. When you will divide both, you will get mu r epsilon r, relative permeability into relative permittivity. In many times questions they won't mention the relative permeability, so refractive index is directly proportional to root under epsilon r. Relative permittivity of medium is known, so you can tell the refractive index of medium. Impedance. Now when an EM wave is propagating in a medium, then the medium will offer impedance against its motion. That impedance Z is defined as E by H. E is the electric field, H is magnetic field intensity, not the magnetic field induction. We have studied H is B by mu for the medium, and E by V is V. So you can directly say mu into V. Now Z can be written as mu and V can be written, just we saw V can be written as 1 by root mu E. So if you substitute, very simple formula we get, but very important, what is that? Z is under root mu by epsilon. Z is under root mu by epsilon. And if you write mu as mu naught into mu r and epsilon as epsilon naught into epsilon r, so you get this as Z naught, which is the impedance offered by vacuum, which is this value. So Z naught into root under mu r by epsilon r, this is called as the impedance offered by a medium. Now total average density due to EM waves propagating in free space. Energy per unit volume, total average density is double of the energy density of due to electric field only, or double of electric or double of magnetic. Means magnetic and electric both are same. It is equals to half of the total. So this total energy density you can write either as half epsilon naught E naught square, which you remember electric field density formula, or magnetic field energy density formula B square by 2 mu naught. So total energy density is equals to B naught square by 2 mu naught and also equals to half epsilon naught E naught square. If you have any doubt, you can replace E naught by, we know E naught by B naught is C, you can replace that and you will see this form will come. Both are equal. So if they just ask you average energy density of electric field, it will be half of these, or average energy density of magnetic field, half of these. Both are equal to each other. Total energy density is written in this form. When you multiply total energy density into speed of light, you get the total intensity of beam in free space, U average into C. Acha. When EMV beam, suppose it falls on a surface, you are seeing I have drawn a cylindrical electromagnetic beam which is falling at an angle theta with the normal to the surface. This intensity of the beam is I, area of the beam is A, and it is striking a surface slant. So area of strike is, we can replace by trigonometry, A striking area can be written as A by cos theta. If the beam makes an angle theta with the normal, striking area will become A by cos theta. Then this beam will exert force and radiation pressure. Pressure will be obtained as I cos square theta by C into 1 plus R. What is R? R is the reflection coefficient of the striking surface. That means how much it will reflect or how much it will absorb the incident beam. So we will see that what I am trying to say here. Radiation pressure is I cos square theta by C 1 plus R. Force which will be acting vertically downwards on the surface will be radiation pressure multiplied by area of strike. Area of strike is A by cos theta, remember this. So as I told, if the beam strikes normally, theta will be 0 degree. So if theta is 0 degree and suppose it is fully reflected means reflection coefficient R is 1. So P radiation will become I by C, inside 1 plus 1 will become 2, so 2I by C. And if the radiation is completely absorbed by a surface, that means reflection coefficient is 0, so radiation pressure will be I by C, very important. Next, EM wave propagation, it obeys the 4 equations of Maxwell, which are actually nothing but the mathematical form of the 4 fundamental laws of electromagnetism. First one is Gauss law for electricity, which you all know, flux is equals to Q enclosed by epsilon naught, electric flux. Next is Gauss law for magnetism, closed integral B dot dA is equals to 0. Faraday's law of EMI, which is integral of the induced electric field, gives d phi by dt, d phi b by dt or a dB by dt for a time varying magnetic field. And Ampere's law, which is modified by Maxwell as integral, line integral B dot dl is mu naught into Ampere had told it is equals to mu naught I, but he said, Maxwell said, instead of I it is IC plus ID. IC is called conduction current, which is flowing in the conductors actually, and ID, which is a sense, not an actual current, it is a sense of change of electric flux. So ID is defined as d phi E by dt, or basically it is to be corrected here, it's not d phi by dt, it is actually dq by dt. And if you go by this law, Q can be written as flux into epsilon naught, so it can be written as epsilon naught into d phi by dt. This is a term which is given a name, displacement current. Now, an example of finding displacement and conduction current and explaining them, when we have a capacitor which is charged by a time varying voltage. If voltage is changing with time, so the charge on the capacitor will also change with time. So as the charge will change, so in between the two plates the electric flux will also change. So here we take a representation ID, which is called as displacement current. So current is not actually flowing, it is the rate of change of charge, and current is actually flowing in the wire, which is rate of flow of charge. This IC is rate of flow of charge, which is called as dq by dt in the wire, whereas ID is rate of change of charge on the surface of the plates, so that is called as displacement current. For maintaining the continuity, we say that when current is flowing in a circuit, this is the gap, nothing is flowing. So to maintain the continuity, we say that IC is equals to ID. IC and ID are equal in magnitude. So IC and ID both are equal, dq by dt. But mathematically both are same, but sense wise one is rate of flow of charge, one is rate of change of charge, or rate of, it is representing rate of change of electric flux in between the plates. So dq by dt, where q is CV. So if you write voltage, suppose sinusoidal V naught sin omega t, so you get both values as C V naught omega cos omega t. So if they ask you what is the peak value of conduction current or peak value of displacement current, you will say C V naught omega, that's it. Also, if they ask you, suppose this line, axis line, you can see this is taken as the central axis of the plates. I am taking at small r equals to 0 and the plate radius is capital R. So they will ask you that if I draw an Amperian loop outside, I want to find at r distance what is the magnetic field outside, and I can draw it inside also at r distance if I am interested in finding the magnetic field. So by using Ampere's law, when we find it outside, the field comes just like a straight long wire mu naught IC by 2 pi r, inversely proportional to r. So at r distance from the central axis, outside the plates, magnetic field is mu naught IC by 2 pi r. But when you find it inside, this ID is in the total area of the plate, which is pi capital R square. So when you are finding at small r, you will find by unitary method in this area pi small r square. So the term comes like this, B is mu naught by 2 pi r small r square by capital R square ID, which can be transformed and written as mu naught into ID, total displacement current, by 2 pi capital R square, where r is the radius of the plate, and multiplied by small r. Small r is the distance where you want to find the field. This formula is to be used in between the plates. So in between the plates, magnetic field is directly proportional to small r, the radial distance from the central axis, and outside it is inversely proportional to the radial distance from the central axis. So these are the important concepts of the chapters which we collectively explained today. I hope it is clear to all of you. So thank you.